Assalamu alaikum warahmatullahi wabarakatuh. So, Alhamdulillah, we have done our test number one. Mashallah, mostly all of you were present and you already submitted, uploaded, except two students. Number one, I know him very well, Mr. Clifson. Clifson, anyway, I'm not bothering him, but the issue is one of the student, he will reappear because he has some general reason. So he will reappear for the test one because test one is under my control, but final assessment is beyond my control. Okay, so final assessment will be on week 14, inshallah, and it will be in DAG hall. Okay, I will book DAG hall for you people. So for final DAG hall, please let me know the time in week 14 because I have to arrange all four group in one go. Okay, so evening, okay, because evening is the most suitable time. Or because week 14 normally you will have final assessments. It's up to you. So if week 14 we have like timings uh, 8 to 12. Okay, so which time is suitable for you? 8 to 12. Okay, it's almost 2 hour test. So either 8 to 10 or 10 to 12. So both are my own classes, 8 to 10 and 10 to 12. I don't know about others. So this will be easy for me if 8 to 10 because 2 A and B section are with me and C and D, they can see how they make possible, how they make it possible. So otherwise it will be in evening, like 5 o'clock, 3 o'clock, 4 to 6 like this. But please, you have to finalize within this week, maybe tomorrow, because I want to book, and it's actually first come first serve basis. If not, definitely I will go for Friday 6 to 8 like this or 5 to 7 like this. So how week 14 if I book 10 to 12. What about section A and B? Is it possible for you? Because week 14 is the last week, mostly you will have final assessment. Or give me any evening time and any evening suitable time. 3 to 5, 3 to 5, Monday, Tuesday, Wednesday, Thursday, Friday. I don't have an issue, okay? Just tell me the time, so I have to finalize. Okay, because I have to book hall by this week. So Alhamdulillah, test one already gone. For section C and D, Dr. Feroz is responsible to give you assignment. And for my section A and B, we already done many tutorials. Number one, I can mark from tutorial, but I already given you assignment number one. You can submit by like next week, 20th of December online. You can submit like on Google Drive. Okay, CR will share the Google Drive, and you will submit. And one more assignment I will give you maybe 8 week 11 or week 10, because then we come physically. So I will give you some word programming assignment. Okay, just easy programs. Don't worry. So Alhamdulillah, everything is going well because we had online classes. My plan was to come with the physical, but okay, test one already done. And hopefully I will give you the 50% marks as soon as possible. Okay, maybe first week of January, I will reveal you 50% marks for section C and D. Whenever she give me the marks, I will reveal. Maybe she will also reveal you, and I will reveal my part, test one. Okay, I will reveal test one. I will disclose test one, and Dr. Feroz will give you assignment marks. So it will be okay. For test one, maybe I will mark within week, within maybe next week. I will finalize. How? Okay. Okay. Let me share the slides. No need to mark the attendance. Thanks to Google Meet, they will share the attendance after the class. So I think we already done lecture number 5, or we can say chapter number 5. Okay. Okay. We have only actually 9 slides. Only 9 slides. Okay. This is 5, and we have still 5 weeks or 4 weeks, so we can easily finish. But the slide number 6 and 7, they are belongs to our lab, not from the theory class. Okay, so after this we have only two slides, and slide number 8 is very simple, only I think 10-15 slides, just you have some performance parameters, very easy. It will take only half an hour. So alhamdulillah, we are on the right track. So we have seen this overview of algorithms and concurrency, and I think task generation we already done, task size of data, characteristics of task interactions, regular, irregular, yes, and then we have done this or not? Anybody?
Dah rasanya.
Sorry?
Yes.
I think yes.
Already did. Already done. So.
Okay, I will repeat, no issue. I will repeat from here, no issue. I will repeat from here. Just give me 5 minutes for pray. I'm just praying here. I will start from this slide, okay? No issue. Tara masala. Yeah, we are done already. I know. So no issue. It can take only few minutes. Just give me 3 minutes. अभी बना के दे ताकि मैं प्रेजेंटेशन क्या बोला पे आप नहीं अब तो मेरा प्रेजेंटेशन तैयार हो गया आपने आईडी क्या खड़े होके आप हर लफ्ज को दोबारा स्माइल करके हर लफ्ज पे ये बताया है ऐसे बोलो हर लफ्ज पे पॉज दो 3 वर्ड्स में पॉज दो आनंदी कोई सारी एक्टिविटी में आपने नहीं करे वो अंदर मेरे चप्पल पड़ा गिरे वाला छोड़ना है सिर्फ ये हर 3 वर्ड्स में पॉज दो रुक के बोलो जल्दी ना बोलो उसमें आपको मिस्टेक्स होंगी और इंग्लिश एक्सेंट बनाओ आर को डब्ल्यू बी को दांतों पे डब्ल्यू को ऐसे कर ताकि अपनी इंग्लिश आपकी है सब्जेक्ट में इंग्लिश है तो आपकी इंग्लिश अच्छी लगे कमजोर इंग्लिश में ऐसा कहते हैं तेज आपको मैंने कहा बस मेरे प्रपोजल में थी चीजें एक्चुअली इवेंचुअली gradually slowly इस सारे वर्ड दे रहे हैं सभी पसंद दे रहे हैं क्या कर रहे हैं आप क्या कैसे होगा कंट्रोल साइड we are significant to the needs for extending the windows. It was a universal of the study. मुझे ग्रुप के अंदर मेरा इंट्रोड्यूस myself करके दे सारा लिख के देता हूँ नहीं किया ना मुझे अच्छा करके आज से मेरा वेरी कनेक्टिंग इसके अंदर मेरा क्या वो आपके पास जो एक चाहे ड्यूटी से ना हाँ सिखा दूँ सर अच्छा मुझे बना के दे ताकि मैं उसे कम से कम 10 मिनट और 5 मिनट को ऐसे बना के चीजों को थोड़ा इसके अंदर छोटी सी प्रेजेंटेशन भी डाल दीजिए Studying, and then some said was not trying. Oh yeah, you know, logo that changes. It's a different. Okay, so Bismillahirrahmanirrahim. Characteristics of task interaction example. Just this is simple example of multiplication of sparse matrix with a vector is a good example of static irregular interaction pattern. So what is going on here? We have task 0, 4, 8, 11, like 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 12, 12 tasks here. So this is basically the matrix, and we are multiplying the matrix. How we show this into task interaction graph? So we can say here task 0. Task 0 basically interact with 1, 4, and 8. 1, 4, and 8. So you can see at 0 on the other end, figure number B. At 0, 0 is directly connected with 1, 4, and 8, and so on. And if you see 1, 1 is directly integrated with 0, 2, 5, 6. So 1, see, you can see 1, 0, 2, 5, and 6. So this is basically a task interaction characteristics or task interaction graph. Okay, understand? Yes, we have done already. So just we can see the interaction, how tasks are interaction with each other. Okay, understand? Okay, good, Bagus. Okay, next, um, characteristics of task interaction. Interaction may be read only and read write. Read only interaction, task just read data items associated with other tasks. So you have to just these are the basically the concepts that you just understand. Okay, so we have different types of things, different types of tasks, different task size, task interaction, its characteristics. So read only interaction just read data items associated with the other task, and read write interaction definitely read as well as modify. Like definitely after you write, you have done something. Okay, some modifications, some amendments, data item associated with other tasks. So in general, real world interactions are harder to code. Okay, read write interaction are harder to code because you have to do twice, read as well as write, since they require additional synchronization primitives. Okay, so you have to synchronize because you are doing read as well as write both the tasks. So it's a bit harder than only read only. Okay, one-way interaction and two-way interaction. One way can be initiated and accomplished by one of the two interaction tasks. Okay, this is one-way interaction because if I talk with someone, I initiate, so it's one way. Two-way require participation for both tasks involves is an interaction. Okay, so this is two-way interaction. So two-way requires participation from both tasks involved in an interaction. That's why one-way interaction are somewhat harder to code in message because there is no acknowledgement. Because there is no acknowledgement in one-way interaction. That's why it's hard. API, application program interface. So now mapping technique. Why we do mapping? I already give you the example of the timetable of like why we make timetable, because we don't have enough classrooms. That's why you come, some come evening, some afternoon, some morning. So we synchronize you people and map your timetable with the lecturers. Definitely we don't have enough time to teach you. We have a limited hours as per like for the Ministry of Education. They give us you have to teach only 2 subjects, not more than 2 subjects. So that's why we have to map. So we have a lot of tasks, hundreds of tasks, but we have limited number of processors. How we map these tasks to limited number of processors? So what we can do, we can assign, like for example, task 1 to 10 done by processor 1, and processor 2 is responsible task 11 to 20, and processor 3 will execute task 21 to 30, like this. In this manner we can map. This is called mapping techniques. Okay, so because we want to save cost. Why we do mapping? Because we want to save cost. So once a problem has been decomposed into concurrent tasks, these must be mapped to processes that can be executed on the parallel platform. So mapping must minimize the overhead. Okay, overhead mean like burden, extra cost. Because in mapping we have to do a lot of things. A lot of things like uh, we have to create a schedule. Uh, understand? It's not easy. So that's why we have to bear some overhead. So we have to minimize overhead, extra work. So primary overhead are communication, the time spent in inter-process interaction. Because if processor one free, if processor two free, we can assign another task. So we have to communicate. This is called inter-process interaction. Idling, the time that some process may spend being idle. For example, some will take more time, some will take less time. So definitely they will be idle. Idle means free, nothing doing anything. Okay. So minimizing these overheads often represents contradicting objectives. So we have to minimize the overheads, the extra burden, the extra task. Assigning all work to one processor, it's nonsense way that we assign. We have many processors and we assign all the tasks to one processor. So primarily minimize communication. Definitely it will minimize communication, but it at the expense of significant idling. Other processors will free. Other processors will free. So that's why we have to do mapping. Why? Because we have limited number of processor and we have huge number of tasks. That's why we do mapping. Like we have limited number of rooms, classrooms, and we have thousands of students. So how we map? We give different timings, okay, different days. So mapping technique for idling, minimize idling. See, these are the two examples, A and B. So if you see A, so mapping must simultaneously minimize idling and load balance. Which one is load balance? Because see, T0 start and T3 end, finish. Figure A, you can see the task 1, 5, 2, 6, 3, 7, 8, 9 properly synchronized with the processor P1, P2, P3, P4, and then 9, 10, 11, 12, and then at T3 finish. But here they give three tasks like P1, 1, 2, 3, P2, 4, 5, 6, P3, 7, 8, and P4 is free. So what happened? 9 will assign to P3 again, and 10, 11, 12 to P4 after this. So what happened? It will take more time. So we have to synchronize properly. We have to assign proper load balance, workload among the processor. So very simple. So task depend the last four tasks, the last four after 3 seconds or 3 minutes, we can say, task can be started after the first 8 are finished. After first 8 finish, then other 4 will start. So definitely this way to map. So figure A is okay, quite balanced. That's why it complete in the less time. So mapping technique for minimum idling, static mapping, dynamic mapping. Static mapping tasks are mapped to process prior to the execution of the algorithm. Before execution of the algorithm, for this to work, we must have a good estimate of size of tasks. We can easily estimate the size of tasks because it's pre-execution. But dynamic is during runtime. The tasks are mapped to processes at runtime. This may because the tasks are generated at runtime or that their size are not known. So we can do like normally we do before execution. This is quite control, but sometimes we have dynamic mapping as well because after execution, like some of the tasks are dependent with other tasks, so it will be synchronized by our algorithm automatically. We call dynamic mapping. So other factors that determine the choice of techniques include the size of data, definitely, associated with the task, and the nature of underlying domain, the application actually. Schemes of static mapping. Three schemes: data partition, graph partition, hierarchical mapping. So data partition, the partition data made during decomposition becomes the partition for the mapping too. The main concern is how to distribute the partition data to the processes. Type of distribution schemes: block distribution, basic concept. Graph partition, simply task dependency graph and task interaction graph is used to find the appropriate partition formatting. So finding optimal mapping is NP hard, it means that difficult to program. Hierarchical mapping, combination of schemes like TDG or data partition or TIG or data partitioning. So data partition and graph already we have seen last lecture. So free here block array distribution scheme. Simply we can do row wise or column wise. The simplest way array distribution scheme for dense matrix are 1D block, one dimensional block, either row wise or either column wise. So it means that we have add process P0 to P7. Or we can say we have like processors in a grid. How we organize the processor, row wise, column wise. An example of block distribution scheme with a higher dimension. This is 2-dimension. So in 2-dimension, the same thing we can go for like 4 by 8, 4 by 4. It's 16 elements. So 16 elements we can arrange 4 by 4 or 2 by 8. 4 row, 4 column, 2 row and 8 column. Here 4 rows and 4 column. Here 2 rows and 8 column. 2 by 8, 16. 4 by 4, 16, simply. So data sharing in dense matrix multiplication, same thing. Like we can multiply one row with the whole matrix and get the answer, or we can row each row by each column and get the answers. It's up to the scheme. Okay. Graph partition based data decomposition. In case of sparse matrix, block decomposition are more complex. Consider the problem of multiplying a sparse matrix with a vector. The graph of matrix is a useful indicator of the work, mean number of nodes, and communication, the degree of node. In this case, you like to partition the graph so to assign equal number of nodes to each process while minimizing edge count of the graph partition. For example, here random partition and partition for minimum edge count. The random partition is very difficult to manage, but here blue, red, green, yellow, all are proper cut edge. We call partition of minimum cut edge. It means that we can assign the same instruction to the one processor. Simply, it's the same type of instructions we assign, or same type of task we assign to any of the processor. It's like this. This is partition for, you see, green, red. It means the same time, same things, or same algorithms, or same equations, or same computation task. Same computation task we assign to same grid. Mapping based on task partitioning. Partitioning is given task dependency graph across processes. Determine an optimal mapping for general task dependency graph is NP hard. Not possible. Complete problem. Excellent heuristic mean algorithm exists for structure graph. So we have like mapping based task partition, like tree structure. Examples illustrate the dependency graph of one view of quick sort algorithm. Same we have done the quick sort in our previous chapter. How we assign to 8 processes. See, 0 to 7. Then the result of 6, 7 assigned to 6, then 4, then 0. Like this is minimum number problem, minimum number. 6, 7, minimum is 6. 4, 6, 4 minimum. 4, 0, 0 minimum. like this. Okay, here sparse graph for computing a sparse matrix vector product, and it's mapping simple thing like C0 is mapped with 4, 7, 6, 7, 8, C1 is 0, 1 to 12, and C2 0, 4, 5, 6. Same thing here. We have seen already sparse matrix, and it's we can say the graph, or we say adjacency graph. Adjacency graph. Below graph is basically adjacency graph. We can see the adjacent of 0, 2, 1 like this. Hierarchical mapping. Sometimes a single mapping technique is inadequate. So we have to do some, we can say, hybrid. For example, the task mapping of the binary tree quicksort cannot use large number of processors. For this reason, mapping can be used at the top level and data partition within each level. So we can make hybrid. We can make like hybrid. Okay, so here, if you see the lower level and we can see the upper level. So lower level, same thing, P0, we can make like P0, P1, P2, P3, P4, P5, and then we add all, and then we finally, we have all the processes. So we can partition our tasks like this. We call it hierarchy. There is a hierarchy basically. Hierarchy mapping. Scheme for dynamic mapping. Why we need this? When static mapping may result in a highly imbalanced distribution. Sometimes static mapping may result in highly imbalanced distribution. So definitely we go for dynamic load balance. So two schemes, centralized and distributed. In centralized, a central process that controls the task distribution, and distributed tasks are distributed among the process. Centralized, there's a central process that control all the task distribution, but distributed already among the processors. Process or processor, same thing. So centralized dynamic mapping, key idea, two kind of process, master and slave. Master process manage a pool of tasks and add a new task into pool, and slave just request when nothing to do and do the work. Disadvantage, limited scalability. When the number of processes increase, the master may become the bottleneck. Solution, to evaluate this, the process may pick up a number of tasks, a chunk at one time. This is called chunk scheduling. 10, 10, 20, 20, 30, 30, not one by one. Centralized dynamic mapping, like master and slave. Distributed, each process can send or receive work from other processes because it's distributed. This elevates the bottleneck in centralized scheme. Centralized scheme, there is chance of bottleneck. Here, there will be no bottleneck. But the challenges, but it's difficult. Dynamic is quite difficult. Challenges are, how are sensing and receiving process paired together? Who initiate work transfer? How much work is transferred already? So it depends upon the application. It depends upon the application, the size of data, the size of task, number of processes, number of processors. Methods of minimizing interaction overhead. So these are the methods. Number one is interaction overhead. We have to minimize interaction overhead. The excessive time spent to exchange message, data, or work between tasks located from different processes. So it's better to assign the same chunk, same computation task to the same processor. It'll be easy. Okay, like 1 to 10, 10 to 20, 1 to 10, one grid. 10 to 11, 10 to 11 to 20 is a second grid. So which we should assign in first grid. Okay. So method to be discussed: maximize data locality, minimize frequency of interaction, how many times, and minimize contention and hotspot. Contention means two processes want to occupy or access the same processor. This is called contention. So method 1, maximize data locality. Number 1 method is to minimize interaction overhead, maximize data locality. Definition of data locality: a concept to use local data. And challenge: the tasks from different processes require access to some common data. Okay, this is a challenge. Example, see the example, very simple. Task A need data X. Task A need data X from task C, while task B need data X from C. See, A need X from C and B need X from C. B also need X from C. So what happened? So how we use this? How we overcome this? Both tasks A and B should have their own local data X. It will be easy. Otherwise, there is a hotspot or contention. Minimize frequency interaction, like the number of interaction. Challenge: the cost taken to start up an interaction between tasks can cause interaction overhead. Example: task A need to access data X, Y, Z, and task B at different time. From task B at different time. Okay, so task A basically need to access data from data XYZ from B at different time. So first A, then Y, then Z. So what happened? Merge multiple interaction to one where was possible. So we can merge all interaction in one because it will get data X, Y, Z from B at one time. We merge multiple interaction in one because we want to minimize frequency of interaction. One time, two time, three kali, uppan kali, lima kali. So why not just come for one time and take all? Minimize contention and hotspot. Like same resource accessed by many tasks. One processor accessed by many tasks. So it will raise the race condition. Race condition will occur. Race condition. We call race condition. Race. Everybody want to win. So example is task A need data XY from C and task B need data XY from C. See? A need data XY from C and B need XY from C. Okay. So what we can do? We can rearrange the order of the tasks. That means first task A axis X and B axis Y. And then task A axis Y and B axis X. Very simple. Okay, farm. Very, very easy. Rearrange the order of the task. A first axis X and B axis Y. And then A axis Y and B axis X. Simple. Okay, so now we have our parallel algorithm models. Very simple, easy model. Algorithm model is a way of structuring a parallel algorithm by selecting a decomposition of mapping technique and applying the appropriate strategy to fulfill certain objectives like minimize interaction. So we have data parallel model, task graph model, work pool model, master slave pipeline, or we call producer consumer model, and hybrid model, combination of any two. So this is data parallel model. Very simple data parallel model. Task decomposition is usually based on data partitioning. Tasks are statically or semi-statically mapped onto processes. Each task performs similar operation on different data. Synchronization of tasks may involve. So example of simply dense matrix multiplication. See the example below the figure. We have a control unit. It will take the instruction stream, process 2, processor 1, process 2, and processor 3, and we have data stream parallelly. See, this is data parallel. So data stream 1 will be go processor 1 handled by processor 1, and 2 will handled by 2, and 3 will be handled by 3, and up so on and so on. Okay, this is very simple model, data parallel model. See, data and the processor. Task graph model. Task decomposition result in a task graph. So task graph information dependency is used to map tasks onto processes. This can assist to reduce interaction. So mapping can be done statically or dynamically. So example, parallel quick sort, sparse matrix factorization, like we have task 1, and then task 1 interact with task 4, it can interact with task 3, and task 2, and task 2 can interact with 5, and task 3 will interact also 5, and task 5 will interact 6, like this, and 4 will interact 6. So like in such a manner, like we have to draw the graph, we can like as a graph model, we can implement this into our actual system. This is called task graph model. This is parallel model, very simple. And this one is work pool. Work pool. Basically, it can be statically or dynamically, but the mapping is based on dynamic mapping of tasks onto processes for load balance. This is basically for load balance. Like mapping can be centralized or decentralized. Example is parallel search tree, where we have a processors and all processes are assigned to the work pool. For example, 1 to 10, 10 to 20, 20 to 30, 30 to 40. We assign to all processors. We have a pool of work, and we assign to the processors. Or we can say chunk of work. And this is master slave manager working model. One manager and all other are subordinate. So master slave process generate task and allocate it to slave. So master is the one who synchronize the task. So master may cause all workers to synchronize. This model can be generated to the hierarchical or multi-level master scale, because we have further like manager and assistant manager, like this executives. So we have different type of slaves under different managers. Okay, or level 1, level 2, level 3. This is only one level, master and slave. Slave process 1, slave process 2, slave 3, and slave 4. And this is last, pipelining or producer consumer. We can do and pipeline like task 1, task 2, task 3, task 4, and task n. And we have a consumer. Producer is basically we have a task, and consumer we have a processor, or we can say the producer is our processor and consumer is our data. So pipeline is a chain of producers and consumers. A sequence of processors form a pipeline. A stream of data is passed through the succession of processes. In a chain, consumer process are those who need the data, and the producer who produce the data, like the processor, the control unit. So pipeline can be linear, chain, or direct graph. The tasks are generated statically. The tasks are mapped onto processes. We have to map the task. Same thing we are doing, but we are doing in pipeline. Step by step, simply step by step. We call pipeline. So basically, now we have programming slides, which is we call lecture 6. So these programming slides we will complete in our respective lab. But I want to show you some basic Okay. Okay, I'm sharing the slides now. Okay. Okay. This is a parallel programming approach. So I already shared the slides. Okay, I just shared the group. Okay. Okay, this is the final group. Okay, here we go. So, parallel programming approach, part one. Part one and part two will be in our lab. Data flows already started. So, we already done something, some installation, some kind of things. So, we will do physically. I will give you the assignment also from the programming side, week 10 or 11. Okay. So, topic overview, types of message passing programming. The building blocks, send and receive operations, MPI, message passing interface, and collective communication operators. We see how broadcast, scatter, etc. Okay, so for my class, section A and B, we will proceed with C, simple C programming. Okay, and for data flows, I think they will do with Java or some other program. I have no idea. Okay, so it depends upon the lecturer. So if you see the logical view perspective, because we have a number of processes, and then each with its own exclusive address space. Okay, so process can communicate with each other. The process can communicate with each other, and processes can synchronize with each other also. And the interaction read only and read write require cooperation of two processes. What is process? The program in execution is called process. So the process that has a data and the process that wants to access the data. So we have nodes, we have a processor, and we have a processes. For example, node 1, we have 4 processes, node 2, we have 4 processes, like this. This is logical view perspective with the processes. So approach of writing MP programs. So most message passing programs are writing using the single program, multiple data SPMD model. Two ways of MP: synchronous, asynchronous, and loosely synchronous. Or in asynchronous, all concurrent tasks execute asynchronously. Reverse. And loosely synchronous, tasks or subset of tasks synchronized to perform interaction. Synchronized to perform interaction between these interaction tasks execute completely asynchronously. We'll see this, how we assign the task, no issue. Just you see that how it works. So synchronous messages, synchronous message involve a client that waits for the server to respond the message. Simply, the client wait for server to respond. Asynchronous, client does not wait for the message to respond from the server. Okay. Okay, so in one, synchronous, clients that waits for a server to respond the message. But here, client that does not wait for message from server. So messages are able to flow in both direction and to or from. Essentially, it means that synchronous messaging is a two-way communication. Sender send message to receive, and receiver receive the message and gives reply to sender, give acknowledgement to sender, and sender will not send another message until it gets acknowledged or reply from the receiver. Have to wait for a task to finish before moving to another task. Very simple. Very, very simple concept. Okay, and asynchronous reward for this. Asynchronous message reward a client that does not wait for a message from the server. An event is used to trigger a message from a server. So even if a client is down, the message will completely successfully. Asynchronous message mean that is a one-way communication and the flow communication in one way only. So can move to other tasks before it finish. So synchronous message and asynchronous messages. Here two basic operation of the send and receive. Very, very simple thing that we have a node, two basic operation. We have send message and the receive message. See, these are the nodes and we have a processes. How this communicate with each other. They can send and they can receive messages within the node or other than the node. Okay. Send and receive operations. The common prototype of these operations are as follows. For send and for receive. For this is for send and this is for receive. So what does it mean? See, this is the beauty to learn the programming language or any of the language. You must understand as it is. For example, if you teach Malay, if you teach English, so you have to use some standards. A mean A, B mean B. You can't say no, I will say B to boo boo, ba bee boo. No, B mean B. And nobody can say, oh, I will write B to be like O O O, 3 O. No, you write 2 O and line. So these are the standards. Words are the standards. You have to use same words. Minam, minam. Malam, malam. Pagi, pagi. Pagi is not poogie. No poogie. Pagi. Malam is not yalam. No. It's malam. So you have to obey. You have to fulfill. You have to just apply. You will never say, oh, no, I will say malam to this and jalan to this. No. Follow. So here, you should follow. For sand, like wide man wide, bracket, see out, see in, you have to use. Here, you have to write sand, static, sand buffer, int, numeric length, number length, and int destination. Okay. And for receive, void receiving buffer, int, num length, and source. Because for sender, you should know the destination. For sender, you should know the source basically and the sender. Source and sender and receiver. Okay. So send buff basically points to a buffer that store data to be sent. And receive buffer basically buffer that stored to be received. That store data to be received. Num length is a number of data units to be sent. 1, 2, 3, how many data units you have to send. And destination, DST is a destination, is the identifier of the processes that receive the data. And source is the identifier of the process that sends the data. Basic operation of message passing programming. send and receive operation. Very simple. So consider the code segment. What's going on here? This is P0, P0, or P1. P0 is a sender and P1 is a receiver. So same thing you can recall here. Here, that sender and receiver. Which parameters? So sender is sending basically 100. And this is ampersand A. This is basically the buffer, sender buffer. And this is one is the data length. Data length. This is one only one. And the last one is the destination identifier. Okay, which is P1, 1. And next, they initialize with a 0. Here, there is some confusion. There is some confusion. We have to fix this. So at P1, receiving end, receive ampersand A, 1 and 0. 0 is the P0. 0 is the source. 0 is the sender. And 1 mean only one data length. One data length. And is the receiver. Ampersand A is a receiver buffer. So what it will print? There is a confusion because suppose P1 should receive 100, but there is a possibility P1 receives 0 because we already initialized with the 0. This might happen if the communication is not appropriately designed. So we have to design properly. We have to design proper communication protocol. For instance, the send operation returned before the communication operation has completed. Thus, this motivates the design of send and receive protocol. So it means that we should write the protocol properly. If I omit this, yes, it will receive 100. Faham? Very simple. Because the control transfer to the next instruction. Next instruction is A is equal to 10 or A is equal to 20. So maybe there's a confusion that it will update the value and then send. Faham? Yes. I want to finish as soon as possible. Just few minutes more. So message passing methods and modes. Two types of message passing methods, blocking and non-blocking. And two communication models, buffered and non-buffered. Blocking means the sender operation blocks until it can guarantee that the semantic will not be violated. The rule will not be violated on return, irrespective of what happened in the program subsequently. This is blocking manner. What happened in subsequent manner? It should send 100. So we should go for the blocking. Non-blocking, the protocol returns from the sender or receive operation before it semantically save or to do so. So it can send anything because we'll see next the example of blocking, non-blocking. And two general communication modes, buffered, a temporary storage at sender receiver, and non-buffered, no temporary storage. Buffer is a temporary memory. So a simple method for forcing send receive semantics, it from the send operation to return only when it is safe. When it is safe. In a non-buffered blocking, send the operation does not return until the matching receive has been encountered at the receiving process. Idlings and deadlocks are major issues with non-blocking buffer send. How? We'll see in the example here. Here, A, B, C. A is basically handshake for blocking. non-buffered send-receive operation. It is easy to see that in case where sender and receiver do not reach communication point at similar time, that can considerable idling overhead, like free. For example, here sender come first, sender send to request, and receive send okay to send. Okay, it send the acknowledgement. So sender come first, idling at sender. Sender will wait. Sender will wait. Okay. And B, sender and receiver come at the same time. Both come at the same time. So here idling minimize. Idling minimize. Sender send a request and wait for the receiver. Receiver send a request. So there is the idling at sender side. If both come at the same time, so there is no idling or minimum idlings. If receiver come first, so it will wait for the sender. So idling at the receiver side. That's why we call blocking non-buffered. So see here, request to send and okay to send both are in same time. That's why if we go next, you can see the all three explanations. A, the sender initiate the sender request and wait for the response. The receiver make a response. The data is copied and transferred to the receiver. And then operation is completed. B, only three steps. Only three steps. The sender initiate the sender and almost the same time the receiver make a response. And the data is copied and transferred to receiver and complete. So here only three steps. A and C are four steps. Because in C, receiver came first. Receiver wait to the make response, the sender make request, and then data is copied and then complete. Okay, so very simple. In B, we minimize the idling time. Blocking buffer, a simple solution to the idling and deadlocking problem outlined above is to rely on buffers at sending and receiver end. The sending simply copy the data into the designated buffer and return after the copy operation has been completed. The data must be buffered at the receiving end as well. Buffer threads off idling overhead for buffer copying overhead. So we need buffer immediately so both sender and receiver can come at the same time. So block buffer here, you can see sender basically what happened here, send the data, and then receiver, what receiver will do, basically if you see A, this is in presence of communication hardware with buffer at send and receive ends. Here we have a communication hardware. If you use communication hardware, it will be expensive. And B, in absence of communication hardware. See, absence of presence of communication hardware, receiving will be fast. Without communication hardware, sender interrupt receiver and deposit data into buffer and receiving end. Here, it will take time. It will take time. If you use hardware, definitely hardware is a good solution, but it's expensive. You see both the sender encounter to send operation, the sender copy the related data into its buffer. Data transfer is passed to dedicated communication hardware. See, the receiver will check its buffer when encounter a receive operation, and then receiver copy the data to respective location. But without hardware, the sender encounter a send operation, the sender copy the related data directly to the receiver buffer. The receiver will check its buffer when encounter a receive operation. The receiver copy the data to respective locations. So here we have a communication hardware, and here we don't have a communication. It will be fast. A will be fast because we have a dedicated hardware, and B, we don't have dedicated hardware in that system. So this is the same example. For example, block buffered message passing operation. we have bounded buffer size. Bound mean limited. Okay, can have a significant impact on performance. For example, if you want to send data 0 to 1000, 0 to 999, P0 to P1. So what happened? We can send easily. This is the sender is the uh, producer and receiver is the consumer. Okay, but what if consumer much slower than producer? If producer is fast and consumer is slow, definitely what happened? Or if consumer is slow and producer is fast, consumer is slow and producer is fast, and vice versa. So this, if we say condition number one, that consumer was much slower than producer, the receiving end is slow. The receiving end is slow than the sender end. P naught is fast and P1 is slow. In simple word, so it will cause buffer overflow and degrade the performance. Thus, the sender would be blocked until the receiver can free up its buffer space. Faham? Very simple concept. Understand? Blocking buffer, if sender is fast, receiver is slow, it will continue sending data, keep sending data. So what happened? The receiver buffer will overflow. So receiver have to tell to stop data for a while. When it buffer empty, it will send request again. Faham? This is basically okay. So deadlocks are still possible with buffering since receiver operation block, because there will be a deadlock. Deadlock means stop. Okay. Non-blocking and non-buffered. The programmers must ensure semantic at the send and receive. This class of non-blocking protocols return from the send or receive operation before it is semantically safe to do so. Non-blocking operations are generally accompanied by a check status operation. Check status operation. When used correctly, these primitives are capable of overlapping communication overhead with useful computations. Message passing libraries typically provide the both blocking and non-blocking primitives. Here, non-blocking, non-buffer send receive in absence of communication hardware, and B is basically in presence of communication hardware. Same thing on the sender side, unable to update data being sent, but here you can say in B, unsafe to read data being received, because here they have a communication hardware, but the issue is non-blocking, non-buffered. If I explain here, you can see the sender initiates the sender request. The sender can continue doing other tasks. Okay. The receiver, because here non-blocking manner, sender will do other tasks. Sender can continue other tasks. So the receiver responds the request. Data is copied and transferred directly to the receiver. The time at the initiation until the completion of transfer is considered the unsafe to update the related data. Okay. Same thing will be here. Sender initiate the sender request. Sender can continue other tasks. The receiver responds the request. Here data is passed to the dedicated communication hardware. Here we have a hardware. And then during that, the sender can continue doing other tasks, because this is non-blocking manner, non-buffered manner. So it will continue with the other task. The time at the initiation until completion of transfer is considered as a unsafe to update the related data. Maybe there is a chance that data can be update, because that's why but we have to do control over this non-blocking, non-buffered. This is a chance. We can say that it can be happen. Okay, so we have to control this. Either we are using communication hardware or without communication hardware. So send and receive protocol, same thing, blocking operation, non-blocking and non-buffered. Now we'll see the actual thing, which is MPI, the message passing interface. MPI defines a standard library for message passing that can be used to develop portable message passing programs using either C, C++, Java, or Fortran. The MPI message passing interface standard defines both syntax as well as the semantics of the core set of library routines. Vendor implementation of MPI are available on almost all commercial parallel computers. It is possible to write fully functional message passing programs by using the 6 basic routines. We'll see the basic routines. So, if you want to write MPI programming, is very simple. Just we will include the MPI library. Okay, we have to include the MPI library. So we will see the basic things. Number one, MPI initialization, MPI init. This is a minimum set of code, minimum set of routines you have to add in the program. Like whenever you write a C program or C++ program, you have to write the header file and then void main void, then you write a bracket, then you have to write cout statement and then semicolon and bracket close or get ch. Here in MPI, you have to do something like MPI init, which is this is initialize MPI, MPI finalize, terminates MPI com size, determine the number of processes, and MPI com rank, determine the labeling, the calling process. Okay, MPI send and MPI receive, send the message and receive the message. So these are the 6 minimum routines you have to add in any program. Okay, just follow. Just you follow A, B, C, D, cat, apple, mango, dog. Follow. What is mango? Mango is mango. Dog is dog. Cat is cat. C-A-T cat. Not C-U-T cut. C-O-T code. No. Understand? So you have to follow. And these are the data types like MPI character, MPI short, MPI int, MPI long, undersign, same things, same C data type. Okay. And this is starting and terminology, the MPI library. MPI init, always to write MPI init is called prior to any calls to other MPI routines. Its purpose is to initialize the MPI environment. MPI finalize is always called an AND. You have to write at AND, the last statement. It means that what you are doing, it end the computation and perform various cleanup tasks to terminate MPI environment. Initialize MPI environment, MPI init, terminate MPI environment, MPI finalize. The prototype of function C, like you write main void. So int MPI init, bracket int argc, argument C, character and argument V with 3 static. So MPI init also strips off any MPI related command argument. We'll see this next. All MPI routine data types and constants are prefixed with MPI, MPI integer, MPI character, like this, like here. So always in data type, the prefix MPI underscore must be there. And you will see whenever you compile the program, you will see MPI success, MPI success. Okay, so communicator concept, the concept of A communicator determines the communication domain for point-to-point or collective communication between processes. It is one of the MPI object with a number of attributes. So communicators are dynamic. They can be created and destroyed during program execution. A process can belong to many different possibly overlapping communication domain. It means that domain concept is a concept of grouping a number of processes. To group a number of processes. Each process in a group is associated with a unique integer rank 0 to n minus 1. 0 start from 0 and n minus 1, like 0 to 10, 0 to 9 minus 1. Oh, sorry, 10 minus 1, which is 9. 0 to n minus 1. It determines basically, it's grouping the process basically. And we can use default communicator, COM world. MPI defined a default communicator called this. Convert this communicator includes all the process. All the process will be included in this COM world. 1, 3, 5, 7, 2, 6, 0 all are same in same communicator. Source and destination. 1 source, 4 destination, 0 source, 2 destination, 0 sender, 5 receiver. Okay, queuing, getting information. What kind of information? Number of processes with the same communicator. Number of processes within the same communicator. Rank of process. The rank of process is an integer that range from 0 up to the size of communicator minus 1. Size of communicator minus 1. Any process with the who can request? Any process with the same communicator can request. We'll see this. Okay, this is basically the basic MPI program. Okay, this is basic MPI program. I will start from this next lecture in our lab class. Okay, I will start from this. What do you mean by MPI? What does it mean? We already seen the here. This is basically the Hello World program. Simply Hello World program. We initialize here and we finalize here. In between, we just use the default communicator, COM world. Okay, and we just define the rank and the size, the process here. And then I will explain each and everything in detail because right now we don't have what I say the Visual Studio. So you have to compile and then you will see how it works. Okay, this is process person D. Out of, for example, we have 4 process, so 1 out of 4 hello world, and then 2 out of 4, 3 out of 4, 4 out of 4 if we have 4 process. If you have 3 process, 1 out of 3, 2 out of 3, 3 out of 3. It means that it will print 3 hello world if we have 3 process. If we have 4 process, it will print 4 hello world. Okay, so rest no need. So we'll see this collective communication, barrier, broadcast, scatter, gather, and reduce. Okay, very simple concept. Scatter, and this is gather, all gather in one. Okay, I already shared this slide with you in the group. So test 1 is already done, assignments already given, tutorial you have already done, alhamdulillah. So now we have a lab. We will focus on the lab last 4-5 weeks. Okay, and definitely we have now face to face, but again tomorrow we have online, so I will let you know because tomorrow I have something. I will let you know before. Okay. Any question? Anything you want to ask?
Sir,
Yes, Ahmad Zabir.
for the final exam, week 14. What topics would be in the test?
Okay, for final exam, the topic will be lecture 1, 2, 3, 4, 5, 6, and 7 not included, 8, 9 only. So only 7 lectures. Now we have only 2 more lectures. Only 2 more lectures. One is very short, and other is bit long. So it will take maybe 2 weeks only.
So 6 and 7 would not be included.
Yeah, it will be no 6, 7 no not included.
What?
6 and 7 lecture will not be included. Okay.
Oh, okay. Thank you, Doctor.
Okay. Anything else? Okay, no issue. If you have any question, you can shoot in WhatsApp group. Assalamu alaikum warahmatullahi wabarakatuh.
Waalaikumsalam, Doktor.
Thank you, Doctor.
Thank you, Doctor.
Salam.
Thank you, Doctor.
Thank you, Doctor.
Doktor.
Thank you, Doctor.
Okay, Doctor.
You are most welcome.
Thank you, Doctor.